So welcome to this masterclass from Cambridge Leadership College. My name is Warwick. I'm one of the Z coaches at the college. So in this masterclass, we're looking at AS level chemistry for Cambridge International exams. And we're going to be working through a structured paper, paper 2 from the winter series in 2014. And as usual, as we go through these masterclasses, we'll not only try and highlight the answers, go through those, but we'll try and pick up as well the comments that the chief examiner makes about the strengths and the weaknesses of students who've taken this exam, the questions that they found hardest, and points that students need to attend to. All right, so this is the paper, and the first question looks at elements in group 2, and wants to consider, as you go down the group, well, you've got to explain this trend in first ionization energies. Well, the examiner has said there are 3 points. You can see there's a mark here of 3 that the students need to work on. And so the explanation here is that going down the group, because we're talking about going down the group, aren't we? Down the group, going down the group. Well, what are the trends as we go down the group? As we go down the group, the outer electron, now remember in group 2 there's 2 electrons in the outermost shell, so we need to be talking about these outer electrons. So the outer electron, first point here, has an increased distance from the nucleus. That's the first point. The second point, as you go down the group, these outer electrons, in addition to having increased distance from the nucleus, are more shielded by complete inner shells. And that combination of the outer electrons being further from the nucleus and being more shielded from the nuclear charge by completed inner shells means there's a reduction in electrostatic attraction and that's the reason that the first ionization energy is decreasing down the group. And the examiner was pointing out that to get the marks here, you must have this outer shell electron at an increased distance from the nucleus, and you must say that these outer shell electrons are more shielded by more complete inner shells, and those 2 factors lead to a reduction in the electrostatic force of attraction between the outer shell electron and the nucleus, and that's the reason for the first ionization energies decreasing down the group. Now, for the second point, you've got to see that compared to the first and the second ionization energies, these are all successive ionization energies, aren't they? There's a big jump to the third ionization energy, and that trend is true all the way down the group. If you look at the discontinuity here, there's always a large difference between the second and the third ionization energy. And so what the examiner is looking for here is that when you go from the second to the third ionization energy, that third electron, and we've got 2 points here, haven't we? That third electron is in a lower shell, and because it's in a lower shell, there's an increased attraction, electrostatic force of attraction for the nucleus. And that's the reason that this third ionization energy is much, much larger than the second, because the third electron compared to the second electron is in a lower shell. That lower shell is closer to the nucleus, and so there's an increased attraction for the nucleus by the third electron relative to the second electron. And one of the things that the examiner picked up was that you needed to be discussing these quantum shells, the main shells. And so the students who were talking about sub-shells or students who were talking about orbitals were using the wrong vocabulary. You must be talking about a main quantum shell here, not the subshells or particular orbitals. And so the examiner was finding that students who were using this kind of vocabulary were not in a position to gain full marks. All right, so we're looking at here a mass spectrum for strontium. And the next step up is to give the full electronic configuration for strontium. Now it tells you, doesn't it, that strontium has mass number 38. So we've got to make sure that atomic number 38. So that's the number of protons, the atomic number. And the number of protons in an element, an atom of an element, is going to be balanced by the number of electrons. So there will be 38 protons, 38 electrons too. And so when we write the electronic configuration, we've got to end up with a total of 38 electrons. So we need to keep writing now. So we've got 1s2, 2s2, 2p6. After that, you're going to have the 3s, and that's filled, 3s2. Then you've got 3p, and then that's filled. I'm going to put the 3d in there, but you need to know that the 4s is filled first before 3d. Okay, so you've got 4s2, 4p6. Now, how many have we got to so far? We've got 10 there, 12, 18, 28, 30, 36. We're trying to get to 38, aren't we? So continuing the pattern, you'd have a 4d, but the 5s, just as we had before, is going to fill before the d. So that's 5s2. Now the 4d is empty. So as far as electron configuration goes, we could take that out. And so, whoops, what happened to my 5s2? So that's 5s2, all right? So that's, if we add all that up, that gives us 38 electrons for the atomic number of 38. And if you just wanted to check as well, because we've started here filling the 5s2, we should be in period 5. And what you can do is you can check back into the periodic table and just see that strontium is in period 5. You can check these if you look up in your data book for the periodic table. So that's a quick sanity check. If you started filling the 5s2, then strontium should be appearing in period 5 of the periodic table. And you can just check that in the data book, and that's provided. So that's a free check that you can make sure that you're getting your 1 mark there. And the examiner said, well, okay, a lot of students got that, but some students were filling in the 4d and putting 2 electrons in there rather than in the 5s2. And that, you just need to remember that as these suborbitals are filled, then the s orbital is filling before the d orbital, just as we did as we counted through 3p6, 4s2, 3d10. So it's the same thing that's happening here. So make sure you fill the s orbital in the higher shell before the d orbital in the lower shell. Okay, so there's this mass spectrum. We've got to say, well, there's 4 peaks. Most students got that right. There's 4 isotopes of strontium. Now, the examiner said that students who lost the mark here, some of them just said there are isotopes of strontium, and that wasn't sufficient for the examiner to account for the 4 different peaks you had to say there were 4 isotopes of strontium. So it's being really very, very specific in your answer. And the other thing that a lot of students did was to misuse vocabulary here and incorrectly write isomers. Now we'll get to isomers later in the paper, but you can see it's, you know, there's those words are superficially similar. Of course, they have completely different meanings. And some students, in their rush in the exam, were adding in isomers here rather than isotopes. You're looking at isotopes, atoms of the same element that differ in the number of neutrons in the nucleus, the isotopes. And then afterwards, there's a fairly straightforward, familiar calculation where you've got to work out the relative atomic mass from each of these relative isotopic masses. Okay, so I mean, it's much easier if I do it here where you can see. So to do this calculation, it's a pretty familiar calculation. You've got to have 0.56% of the relative isotopic mass of 84 plus 9.86% of the relative isotopic mass of 86 plus 7% of the relative isotopic mass of 87, and you've got the majority here, 82.58% of the relative isotopic mass of 88. So if you do that calculation, you've just got to sort of punch quite a few buttons on your calculator. You end up with the relative atomic mass for strontium. And if you do that on your calculator, you end up with a figure of 87.71. But the examiner is saying, look, you might have calculated that because you've got 2 decimal places here, but you've got to give the answer, where is it? You've got to give the answer to 3 significant figures. All right, so the examiner is expecting an answer there of 87.7. That's 3 significant figures. And students lost a mark, actually, if they put this value down, which was the result of the calculation, and didn't gain full marks for putting the 3 significant figures here. And that's a recurrent theme that the examiner identified, was that students under exam conditions are rushing, and they're not giving time to read accurately these question stems. So you can imagine you're in an exam, you do the calculation, you get that, you put it in the answer box there and you move on, but don't forget to read with, read accurately that you've got to give an answer there to 3 significant figures. Okay, so oxidizing agent. So oxidizing agent accepts electrons from another species. Now you remember your mnemonic, oil rig, oxidation is loss, reduction is gain. Well, an oxidizing agent is oxidizing something else. So the thing that's being oxidized must be losing electrons. So the oxidizing agent is being reduced, so it's gaining electrons. So the oxidizing agent gains or accepts electrons from another species. We're just trying to get some accuracy in your language there for 1 mark. Okay, this was another question that was done well by students. You're told the composition by mass is that, and so you have to work out the empirical formula here. Of course, you do that by first of all saying the mass of each element in 100 grams, because this is percentage here. We actually need to work with real masses. So for barium, there's 45.1 grams. For chlorine, there's 23.4 grams. And for oxygen, there's 31.5 grams, because we've got masses. Now, we've got to convert from masses to amount, the number of moles. And to convert from mass to amount, you have to use amount, the number of moles, is equal to the mass divided by the molar mass. And you can look up the molar mass in your data book. You work out, you can just read that straight off from the relative atomic mass and just change the units to grams per mole. And then you can do that division there, the mass divided by the molar mass, and you end up with these amounts. So 0.3284 moles for barium, 0.6601 moles for chlorine, and 1.969 moles for oxygen. So you've got those amounts, and then to compare those amounts, you've got to divide through by the lowest amount to give yourself ratios. And when I divide through by that value there, which is the smallest amount, I get a ratio of 1 for that, 2.01 for that, and 5.99 for that. But because we want an empirical formula, where we'll have a formula with whole numbers, we've got to look at this ratio and decide what the whole numbers are. It's pretty clear that that's 1, that's 2, and that's 6. And so the empirical formula will be barium, and we don't need to write the 1, that's implicit. Chlorine, there's 2 moles of that, and for oxygen, there were 6. All right? So that's that question the examiner said was generally well done by students. I think that's quite a familiar calculation for students to do. Now this next one, we're looking at the reactions of magnesium, a group 2 element. And these reactions, of group 2 elements, are appearing in these Cambridge International exams again and again and again. So, it's an area that students really, really need to learn, because as we go through these masterclasses, we're seeing that group 2 chemistry is coming up again and again and again. And you've got to label or identify these various substances. When magnesium reacts just with water, then you make magnesium hydroxide. Okay? This question stem is asking us for formulae. And when magnesium reacts with steam, then you get a different product. You get magnesium oxide. And then when you react magnesium with nitric acid, the result of that is magnesium nitrate. And these should be all fairly easy formulae to get. So actually, I think that's 3 easy marks there if you know your group 2 chemistry reasonably well. It's an area that all students need to properly revise, because it's coming up again and again in these Cambridge International exams. All right, so we've got to think of a reagent to convert magnesium oxide into magnesium nitrate. Well, again, I think these are easy marks, aren't they? Another 2 marks. The reagent is nitric acid, HNO3, and the equation is you've got the magnesium oxide and you've got the nitric acid, and we know that that's making magnesium nitrate. And you should have learned at GCSE that when an oxide reacts with an acid, it makes a salt and water. That's a standard acid reaction with a basic oxide. So we've got water to go there. And you've just got to balance that equation. Well, you're just going to have 2 moles of nitric acid. And that gives you your balanced equation. Okay, now you've now got to say how you convert this reactant, if it was a solid, back into magnesium oxide. And one of the things that, again, appears again and again and again in these Cambridge International exams is the thermal decomposition of group 2 nitrates. So you've got to heat solid magnesium nitrate, and that'll undergo thermal decomposition to give you back magnesium oxide. Got some more equations to do now. You've got the reaction with water at room temperature. So you've got magnesium plus water, and that's going to the magnesium hydroxide, if you remember. This is not steam, this is with water, and hydrogen gas. And one of the things that the examiner pulled out again and again for many students was that a lot of students were giving these equations and then rushing on to the next one and failing to balance these equations. So make sure you don't miss putting in the stoichiometric coefficients and balancing the equations. Now, this last one here, you've got to look at the thermal decomposition of a group 2 nitrate. So there's only one substance on the left-hand side of the equation. And this is just something that appears again and again in these Cambridge International exams. When you heat the group 2 nitrate, you're going to make the oxide, you're going to produce brown nitrogen dioxide gas, and you're going to produce oxygen gas. And to balance that up, you've got to have 2 of those, and 4 nitrogen dioxide. This is all learning about group 2 chemistry. There's no real shortcut to it. It's got to be learned, and the learning investment that you make has a very high return, because these questions about group 2 chemistry, particularly the thermal decomposition of group 2 nitrates, is a very familiar question in the Cambridge International exams on chemistry. Okay, next up, looking at the manufacture of sulfuric acid. And one of the starting materials, or the materials that's used, is sulphur dioxide gas. And the examiner is asking, well, if you take an iron ore, this iron pyrites, okay, and you roast it in air, well, what's the reaction? Well, we know we're producing sulphur dioxide. And it says iron 3 hydroxide is produced. Well, what's iron 3 hydroxide? Well, that's going to be an iron 3 plus, isn't it? An ionic compound between the iron 3 plus, iron 3, and the oxide ion, which is O2 minus. So the ionic compound that's formed between that cation and that anion is Fe2O3. So that was the thing. You had to take this systematic name for the iron oxide and work out what its symbolic formula was. So that's one step. I suppose you might be getting a mark for that. The next step, of course, is to balance the equation. And again, the examiner is saying that students are losing marks because they're writing down the symbol equation, as we've done, but haven't balanced it. Now, different people will have different ways of balancing equations. The way, if you're really stuck, you can't sort of see it intuitively, is to say, well, you start balancing with the element that appears least in the products. Well, let's look at that. So we've got the iron, we've got 2 of that. The oxygen is appearing both there, and sulfur is just there. There's only 1 of that. So the element that appears least in the products is sulfur, and that's a good place to start when you're balancing. So let's follow that rule then. We've got 1 sulfur here, we've got 2 over here. Well, to balance that, we'd need 2 sulfurs there. Now, so the sulfur is balanced. Now the next atom that appears the least in the products is iron. Well, there's 2 there, so that must mean we've got to have 2 over here, doesn't it? But that means we've doubled up the number of sulfur atoms, so we need to keep balancing. And now, if you do that, we've got 4 sulfur here, 4 sulfur there, 2 iron atoms here, 2 iron atoms here. It's looking good. And we've got that far by choosing in the products the atoms that appear the least and starting to balance those first. Well, all that remains then is to tidy up with oxygen. Now we've got 4 lots of O2 here, which is 8, and you've got 3 oxygens here, so that's 11 oxygens altogether, 8 plus 3. And I suppose you could at that point say, well, that's 5.5 O2 molecules. Well, really we should be giving whole numbers when we're balancing these equations. So let's multiply through by 2, and that gives us 4 of the iron sulfide. And then we've got rid of our half there, haven't we? So now we've got 11 O2, and we've multiplied through by 2 here. You've got 2 Fe2O3, and then you've got 8 sulfur dioxide. So that's, that looks a pretty nasty equation to balance, but we found that wasn't too difficult because we applied that rule of starting with the atoms in the products that occur least in the chemical equation. We started with sulfur, then we worked with iron, and once those were balanced, it was pretty easy to balance up the oxygen and then get rid of any half stoichiometric coefficients. All right, so now, once this sulfur trioxide has been made, well, why don't you just mix that direct with water to make sulfuric acid? And so the examiner is looking for 2 points here that if you just put sulfur trioxide into water, then the reaction is too exothermic. Too much heat is produced, and you get a mist, or you get a fog, you could say, of acid fumes. Now that's dangerous, so you don't want to do that. So instead, you do 2 steps. The first is to take the sulfur trioxide that you've made and react that with some sulfuric acid, and that just goes to this substance here, which is called oleum. And then once you've got your oleum, you're going to dilute that with water. And that gives you the sulfuric acid that you want. But make sure that you're balancing the equation, because again, the examiner was saying, well, students got these equations, but they didn't balance them. And so students might have put this down without balancing, would have got 1 mark rather than 2 marks that are available. Okay, so sulfur dioxide, sulfur trioxide contain sulfur double bonded to oxygen. Well, sulfur, you see, has 6 electrons in the outer shell. Now, if it's double bonded to oxygen, then that sulfur has used 1, 2, 3, 4 of the electrons in its outer shell, and it's got 2 remaining. With sulfur trioxide, then the central sulfur atom has used 1, 2, 3, 4, 5, 6 of its outer shell electrons, and so there's no lone pairs of electrons on the sulfur atom in sulfur trioxide. Now, you can quite easily see, can't you, there, that that bond angle is going to be 120 degrees because you've just got equal repulsion between bond pair, bond pair, bond pair, bond pair, bond pair, bond pair. And so the shape there is going to be trigonal planar. But you know from your electron pair repulsion theory that lone pair, What's happened to my menu? Okay, there we go. That your lone pair bond pair repulsion is stronger than your bond pair repulsion. And so that means that this lone pair bond pair repulsion is going to be stronger than the bond pair repulsion, which means that these two bond pairs here are going to be forced inwards a little bit like that. Okay, so what's happening is that there's a bond angle there of 120 degrees, which is being squashed, which is being reduced because of the lone pair bond pair repulsion, which is stronger than the bond pair repulsion. So that bond angle there is less than 120 degrees. Now, how much less than? Well, you've got to estimate this, and a rule of thumb is to say for each lone pair that you're using in the repulsion, you can subtract 2.5 degrees. It's just a kind of rule of thumb to help you in these calculations. So we would estimate that the bond angle here is 117.5 degrees. And so we've kind of got ahead of ourselves a little bit here. So the SO3 shape was trigonal planar. This shape here, well, you don't need to look at the lone pair of electrons there. That shape there is V-shaped, isn't it? And the bond angle over here, that was a straight 120 degrees. And over here, we need to put, sorry, I've got that the wrong way around, haven't I? I've got the bond angle is less than. So less than 120 degrees, we think about 117.5 degrees. And in the mark scheme, the examiner was happy to accept anything from 115 through to 119 degrees. So we're bang in the middle of that range there. Good. Now, the examiner said, well, the students have got a spot. You've got quite a large space in the exam paper here. You've got 4 marks, and you've got a couple of command words that you've got to look out for. So the command words are state and explain, and you've got to reference Le Chatelier's principle, and you've got to reference reaction kinetics. So that's where your 4 marks are going. For Le Chatelier's principle, state and explain, 2 marks. For reaction kinetics, state and explain. That's your other 2 marks. So you can see, if you pay attention to the question stem, you can work out the allocation of marks. All right, so for the advantage of using 400 degrees Celsius, the advantage that you're going to state is that that equilibrium is established faster. You have to excuse my writing, you can hear on the audio. The equilibrium is established faster because both forward and reverse reaction rates increase. Okay, so you've stated the advantage. Position of equilibrium is established faster because both the forward and reverse reaction rates increase. And the explanation for that is that particles move faster and so have more collisions and more successful collisions, because that's what's happening when you increase the temperature. More successful collisions. Why do they have more successful collisions? Because the kinetic energy of the collisions is great. There's a greater proportion of molecules that have a kinetic energy of collision which is greater or equal to the activation energy. So that was our advantage. We stated and we explained. And for our disadvantage, we're going to state, according to Le Chatelier's principle, that increasing the temperature favors favors reactant, not product. So the disadvantage is that reactant is favored over product, leading to smaller yield, because according to Le Chatelier's principle, when the reaction is exothermic, which we saw earlier in the question, because with an exothermic reaction, when the temperature increases, then the equilibrium position shifts to the right. Sorry, shifts to the left, shifts towards the reactants. Okay, so next one we've got to look at the equilibrium constant in terms of, can you see P in terms of partial pressures? All right, so that means that you've got to write an expression here for the reaction that we had, which was balanced, if you remember. And so you're writing the equilibrium constant in terms of partial pressures as the partial pressure of the sulfur trioxide, and because you've got a stoichiometric coefficient of 2, that's going to be squared, over the partial pressure of sulphur dioxide, that has a stoichiometric coefficient of 2, you're going to square that, times the partial pressure of oxygen, and you don't need to have any indice there because the stoichiometric coefficient is implicitly 1. Now, the examiner pointed out that students were expected to write the equilibrium constant in terms of the partial pressures, and a lot of students accidentally use square brackets, which of course has nothing to do with partial pressure, but is the convention for expressing concentration. So make sure that when you're writing an equilibrium constant in terms of partial pressures, that you use this kind of notation, and don't use the square brackets, which are the convention for indicating concentration. Using square brackets would give you an equilibrium constant in terms of concentrations, Kc, and that's what you don't want to do on this occasion. Now, this part here was one of the questions that students found the hardest, according to the examiner. And it's true that it's hard unless you follow a good system. And so the system that you can follow here, something you can look up, is called an equilibrium table. I'll explain what that is in a moment, but let's get the reaction down. First of all, we've got, this is the balanced chemical equation. And so with the equilibrium table, you've got a mnemonic of ICE, which means initial, change, and equilibrium. So you're looking at your initial amounts, that's the I in ICE. And the question stem tells you that. The initial amount of sulfur dioxide was 2 moles, and the initial amount of oxygen was 2 moles. And of course, initially, no reaction has happened. There's 0 moles of sulfur trioxide. So that's I for initial. C is for change, and it tells us in the question stem here that once we reached equilibrium, then the change as far as the sulfur trioxide was concerned was we'd formed 1.80 moles. Now, so just balance that up. So you can see here you've got, oh, I didn't balance it, sorry. So you've got the same number of moles of sulfur trioxide as you have of sulfur dioxide. And so if you've made 1.80 moles of sulfur trioxide, then you must have reacted 1.80 moles of sulfur dioxide. So that's pretty easy to show with the change is plus 1.8 sulfur trioxide minus 1.8 of sulfur dioxide. So that just leaves the oxygen. If you look at the stoichiometry, the amount of oxygen is half the amount of sulfur trioxide. You've got a stoichiometric ratio of 2 there and 1 there. So if in this process 1.8 moles of sulfur trioxide were made, then you must have 0.9 moles of oxygen that have been used up. It's half of that, isn't it? So that's the initial, that's what's changed, and the E stands for, well, what are the amounts at equilibrium? Well, the amount at equilibrium in the question, we were told that, and we can work out the equilibrium amounts of sulfur dioxide and oxygen just by subtracting the change from the initial amount. So the equilibrium amount of sulfur dioxide is 0.2 moles, and the equilibrium amount of oxygen, doing that subtraction there, is 1.10 moles. So that's that way in of getting these equilibrium amounts using this equilibrium table of having an initial row, a change row, and then working out an equilibrium row is called an equilibrium table, because you've got these 3 rows and these 3 columns. It's a table. Okay, so that was the hard part, actually. And then once you've got these equilibrium amounts, you can total up the total number of moles. You can see you've got 1.8 plus 0.2, that's 2 moles, plus 1.1. So your total amount, if we add everything together, is 3.1 moles. Now once you've got the total, then it's very easy, isn't it, to work out the mole fraction for each of these reactants and products. And so the mole fraction for sulfur dioxide is 0.2 divided by 3.1. And the mole fraction for oxygen is 1.10 divided by 3.10. And the mole fraction for sulfur trioxide is 1.80 divided by 3.10. So those are all our mole fractions. To work out the partial pressures, you multiply the total pressure, which is given to us there, by each mole fraction. So you can work out the partial pressure there, the partial pressure there, the partial pressure there. And once you've got the partial pressures, then you're ready to substitute them in to the equation that you wrote up here. These are the partial pressures of sulfur trioxide squared, the partial pressure of sulfur dioxide squared, the partial pressure of oxygen. Put all those in, do the calculation, and you end up with a result of 1.13 times 10 to the minus 3. And you're just going to work out units as well. Just be careful at this point. So the units, because these are partial pressures, the partial pressure is measured in pascals. So if you had that expression for Kp, then you've got pascals squared at the top, haven't you? And you've got pascals squared in the denominator and times pascals. So that's going to cancel, that's going to cancel. The units here is going to be reciprocal of pascals, or pascals to the minus 1. So your units there are pascals to the minus 1. Now you can see this is actually a mark-rich question. There's 5 marks here. Yeah. Well, getting 1 mark for the units is pretty easy, and the rest students lost a lot of marks, and that's unnecessary, because if you just use one of these simple equilibrium tables, it's very straightforward to work through this initial change in equilibrium amounts. From the equilibrium amounts, that's the hard work done. then work out the mole fraction, work out the partial pressures, substitute the partial pressures into the equation, do all the work on your calculator, and you work out the result. So that's a lot of marks up for grabs there, and students aren't using those equilibrium tables to get those marks. Okay, we're into organic chemistry now, and you've got basically in this question here, you have to read it quite carefully. There's a lot of clues about helping you identify these 4 compounds, P, Q, R, and S. All right, now, so you can read through all the clues, and they're going to react all of these with hot concentrated acidified potassium permanganate. And the reaction you've got to know there is that when you've got a double bond like that, the reaction with acidified potassium manganate, hot concentrated, is going to give you the corresponding carbonyl compounds. Like that. You're breaking that alkene double bond there to give yourself the respective carbonyl compounds. Now, if one of those happened to be just a hydrogen atom there rather than one of these R groups, then you end up with that carbonyl compound not being a ketone, but being an aldehyde, don't you? Like that. And if both of them are hydrogen atoms there, then you end up with making carbon dioxide. All right, so that's the way into this question to know, and this is just learning that you have to do about organic reactions in the Cambridge International Exam syllabus, that when you use hot concentrated acidified potassium manganate 7, then for these alkenes, you're going to break the alkene bond and you're ending up with these carbonyl compounds. Could be a ketone, could be an aldehyde, or in the case of just having 2 hydrogen atoms here, ending up with carbon dioxide. And that's where you're getting these values here coming in, carbon dioxide. Okay, all right. So if you work on all of that, you've got some other clues up here. Well, you know these compounds readily decolorize bromine, so that was our clue that we're working with alkenes, double bond. And we've worked out the reaction here with hot concentrated acidified potassium permanganate. 2,4-dinitrophenylhydrazine, well, that gives you these orange crystalline products with carbonyls, either an aldehyde or a ketone. But only aldehydes will react with Fehling's reagent. All right, so this product S here is a carbonyl, and it does not react with Fehling's, so therefore it's not an aldehyde. Because it's a carbonyl and it's not an aldehyde, it must be a ketone. So that's the kind of thinking that you've got to work through here. And so what you end up with is, if I just draw out the displayed formula for all of these, so P is this. Q is this one. And you can see why both of those reacted to give carbon dioxide, can't you? Because you just had these hydrogen atoms here. And even though they've got this double bond, they don't form these geometric isomers, these cis-trans isomers, because you've got just hydrogen atoms here and here. And then R, of course, is now I'm drawing the trans isomer there. Of course, there is a geometric isomer, there's a cis isomer, because you've got different groups attached to the carbon atom here. You've got H and CH3, H and CH3. So those are the displayed formulae, but you're being asked, aren't you, to give the structural formulae, all right? Now, if we take P up here, then the structural formula is going to be that carbon there. And the examiner is saying that when you write your structural formulae and you've got an alkene, you should include a double bond. So there it is. And that's joined to a carbon atom there. And you know, this is it's a propene derivative, isn't it? And because that's the longest carbon chain, and that's a substituent methyl group, you should put that substituent methyl group in brackets. So the examiner is expecting to see CH3 there, and then continuing along the chain, expecting to see CH3 there. So when writing these structural formulae, if there's an alkene, give double bonds, and if there's a substituent, which is not the main chain, then that goes in brackets. And so you get, let's have a look at Q, then this one over here. Again, you've got that, haven't you? And then you've got your double bond, and then you've got your CH, and then you've got your CH2, CH3. And for R, you've got CH3, you've got CH, and the examiner is wanting you to write in the double bond for alkenes, and then CH3. And so those are the three structural formula that we've worked out by looking at these displayed formula here. Now, where was P? Now, when that reacts with this hot concentrated manganate 7, well, we're getting CO2, and the other carbonyl it's forming is that propanone, isn't it? And so to give the structural formula for that, you can write, excuse me, you've got two methyl groups, and you've got carbon joined to the oxygen for the carbonyl group. Okay, so we had to think about stereoisomerism and geometrical isomers already. So we've been thinking about that, haven't we? And this one here is the one that can exhibit geometric isomers. And we have to explain this parent term, stereoisomerism. And the points that the examiner is looking for there is that when you have stereoisomerism, you have molecules which have the same structural formula, or the same structural formulae, but different spatial arrangement of bonds. Okay, so here's R, isn't it? So that it's got one structural formulae, but we can draw displayed formulae which show a different spatial arrangement in two different geometric isomers. And that's what we have to do next. And the examiner has emboldened this command here to use displayed formulae. Now, when you do displayed formulae, that means that you've got to show every single atom and every single bond. So you could have done this. Okay, that's the cis isomer, isn't it? Actually, what I'm going to do there is just make sure it's absolutely clear that there's a carbon-carbon bond there. Can't get that wrong. Now, the examiner was saying, well, okay, a lot of students wrote that, but that's not really, it's not strictly a displayed formula, because the displayed formula shows every single atom and every single bond. So students lost marks for doing that. You've actually got to show all the individual bonds from carbon to hydrogen. So the examiner is expecting to see these here. So that's the cis isomer, and the trans isomer, again, is going to have the carbon up here and the hydrogen atoms there. And then you've got the carbon atom down here and the hydrogen atoms bonded here. So for these displayed formulae, you must show that the, sorry, yeah, that's right. So you must show every single atom and its bond. Now, this one is cis, they're on the same side, and this one is trans. They're on different sides of the carbon-carbon double bond. And the longest chain is 4 carbons long, isn't it? So our stem is going to be bute, and the functional group is the alkene here, and that's at position 1, 2. So the name for this is but2ene. It's the same for this one as well, but this is cis but2ene, and this is trans but2ene, isn't it? Good, so now we've got to hop back and look at S. That was a ketone. How do you reduce a ketone back to a secondary alcohol? Well, your reagents are either lithium aluminium hydride in dry ether, or you're using sodium borohydride in water methanol. And when you reduce a ketone, you get a secondary alcohol, and that secondary alcohol, if you take the ketone, it's this, isn't it? That's the ketone that we had, and when we reduce it, then we end up with this secondary alcohol here. Okay, now they're just asking us to name this product here, so let's be careful on that. We've got a stem, the stem is 3 carbon atoms long, so we're going to have prop, aren't we? And we've got the alcohol here, so it's going to be the suffix is going to be ol because it's an alcohol, and then we number the chain 1, 2, 3, so that's propan-2-ol, isn't it? So the answer there is propan for the stem, the position is 2, and the functional group suffix is ol, the alcohol. Okay, still going strong on organic chemistry. Again, the critique from the examiner was that students wrote equations. We've got carboxylic acid here, propanoic acid, and the examiner is saying you can just use H to represent reduction. And that gives us, we're reducing carboxylic acid when you get the corresponding alcohol. And water. And students might have got a mark for that, but there's 2 marks available here. And so, the examiner is saying so many students rushed through this and they didn't balance the chemical equation. And it's really, you're just missing marks easily if you rush through and you forget to balance. So that's the balanced equation. And that was a reduction, wasn't it, of a carboxylic acid to an alcohol. Now the opposite of that, going from the alcohol to the carboxylic acid, well, that's not a reduction, it's an oxidation. I think that's an easy mark there. And suitable reagent, well look, in these questions they ask for reagent and conditions. So there's 2 marks here. You can see you've got to specify the reagent and the conditions. Now, for oxidation of alcohols, your reagent is potassium dichromate, or sorry, potassium chromate 7. So the word is okay, potassium chromate 7, or the formula is okay. That's the reagent that's going to do the reduction. Sorry, that's the reagent that's going to do the oxidation. It's an oxidizing agent. And for conditions, you need to talk about anything that you need to add, like a catalyst, the temperature, and normally you'd need to indicate whether the conditions are under reflux, if you want a reaction to go to completion, or distillation, if you want to remove a product as it's made. Now, with this process, you really have to do it under reflux, because when you oxidize an alcohol, the first step in the oxidation is to form an aldehyde, and the second step in the oxidation is to oxidize the aldehyde to the carboxylic acid. So you definitely don't want to be doing distillation. You've got to be doing the reaction under reflux and keep it going until you've got full oxidation of the alcohol through the aldehyde to the carboxylic acid. So that's the reagent, and the conditions are reflux, and it's going to be heated under reflux, and you also need to acidify to make the that's one of the reaction conditions. Okay, so that gave you 2 marks, and funnily enough, this question here, the examiner highlighted as the hardest question in the whole of the paper, which it really, really shouldn't be. Because, look, this is just GCSE knowledge. What do you do when you react calcium carbonate with an acid? If that was a GCSE question, you'd say carbonate and an acid, what would you say? It would make a salt plus water plus carbon dioxide. Now, that's classic GCSE chemistry, and it's no different here, except instead of taking a GCSE familiar acid like hydrochloric acid, you're working with a different acid, propanoic acid, but the principle is the same. And so you've got your calcium carbonate, and you're going to react it with propanoic acid, and you're going to make a salt plus water plus carbon dioxide. And the salt that you make, remember that calcium is calcium 2+, and the anion that you get, the conjugate base from this propanoic acid, is it's a monoprotic acid, isn't it? So the anion is that anion. So because that's got a negative charge, and the calcium in the salt has a 2 positive charge, you're going to need 2 of these anions for each of the calcium cations. So let me just take that back to where it was. That's the propanoic acid, and you're going to have 2 of these propanoate anions to balance the 2 positive charge on the calcium cation. So you've done your hard work. You've just used your GCSE knowledge, but you've used it in an AS level context. And again, the examiner is saying, well done, but a lot of students are losing a mark here because they're not balancing the symbol equation. So don't forget, you've got to get your stoichiometric coefficients correctly done, and just put a 2 in there to balance that equation, and you get full marks. Step 3 was, look, this is an alcohol here, there's an ester over here, there's an esterification going on, and so suitable reagents for step 3, because it's an esterification, is to use ethanoic acid. And again, we've got 2 marks here, and we're asking for reagent and conditions. And so is this going to be done with reflux or distillation? There's no reason to separate out a product as it forms, we can just use reflux. And to make the reaction proceed under reflux, we're going to need to heat it. And the other condition here is that you're going to need some concentrated sulfuric acid, and that's just something that you have to learn. Now, an esterification reaction, when you have ethanoic acid, is an elimination reaction, and the small molecule that's eliminated is water when you do that esterification reaction. So there's 1 mark for that. Okay, well that gets us to the end of the paper. The overall comment that the examiner had here was that students were losing marks balancing equations. They're rushing through, they're not balancing equations. So make sure you attend to that. Some things that appear difficult are actually much easier than you think. For example, working out an acid with a carbonate, that's GCSE knowledge, shouldn't be difficult. It turned out to be the hardest question in the exam. And then the other really hard question was this one earlier on about equilibrium amounts. Again, it shouldn't be hard if you're using this technique of an equilibrium table to lay out the initial, the change, and the equilibrium amounts. And once you're there, the rest of the question falls out easily. So that's just a technique for answering those kinds of equilibrium questions. All right, so that's our masterclass on AS level chemistry from Cambridge Leadership College. And of course, the Z coaches from the college are active on Slack channels. And if you have any questions about the paper, then use the Slack channel and follow up with the Z coaches, and they'll be delighted to take your questions on this paper or on other work that you're doing, and follow up with you on the Slack channel. And so it just remains for me to say thank you for joining the masterclass, and I wish you every success in your studies for Cambridge International Exams AS level chemistry.